Hi, everybody. It's Professor Mitchell, continuing with Chapter 6. In this video, we'll look at Section 6.4 on conditional probability and independence. In this section, we will look at conditional probability of equally likely outcomes, the product rule, independence, and independence of a set of events. Let E and F be events in, little typo there, in a sample space S. The conditional probability, which is read probability of E given F, is the probability of event E occurring given the condition that event F has occurred. In calculating this probability, the sample space is restricted to F. So the formula for the probability of E given F is the probability of E intersect F divided by the probability of F, provided that the probability of F does not equal 0. So we'll look at this example in a couple of different ways. I will show you how to do it using the formula, but I'm also going to show you something else that might make it a little more intuitive. 20% of all the employees of Acme Steel Company are college graduates. Of all its employees, 25% earn more than $50,000 per year, and 15% are college graduates earning more than $50,000. What is the probability that an employee selected at random earns more than $50,000 per year, given that they are a college graduate? So before I show you how to do this using the formula, let me show you the more intuitive approach. For that, I'm going to switch over to my tablet. So what you see here is sometimes called a contingency table. On the left side here, these letters stand for college or no college. And across the top, I have less than 50,000 or more than 50,000. So I've gone ahead and filled in the information that was given in the problem. It said that of all employees, 20% were college graduates, 25% earned more than 50,000 a year, and it said that out of the it said that 15% of the employees were college graduates who earned more than $50,000. Okay, I almost said that wrong. All right, so there is actually enough information here to fill in the rest of these boxes and also the rest of the totals. For example, if there are a total of 20% of the employees who are college graduates and 15% of the employees are college graduates who earn more than 50,000 a year, then that must mean that 5% of the employees are college graduates who earn less than 50,000. Similarly, 25% of all employees earn more than 50,000 a year. 15% are college graduates who earn more than $50,000. So the remaining 10% must be non-college graduates who earn more than 50,000 a year. Now let's see, in order to do the rest of this, I have to fill in some more totals. If 20% of all employees are college graduates, that means 80% are not. And that means I can pop over here and say that this is 70%. And then finally, the percent of employees who earn less than 50,000 a year must be 75%. Notice that checks out two different ways. It's the total of these two numbers, and it also makes these two numbers add up to 100%. All right. Now the question was, what is the probability that an employee earns more than $50,000 a year, given that they are a college graduate. So the intuitive approach to this is to just ignore, think of your sample space as just these people here, and ignore these people. So if that circled area is my whole sample space, I see 15% who earn more than $50,000 a year out of 20% total. So intuitively, this probability should be 0.15 over 0.20, which comes out to be 75%. Okay. So given the fact that the person is a college graduate, the probability that they earn more than $50,000 a year is 0.75. So now let's go back to the presentation, see how to do that with the formula. Okay. So let H be the event that the person earns more than $50,000 a year, and C be the event that they are a college graduate. From the problem, the probability of H is 0.25, the probability of C is 0.20, and the probability of H intersect C is 0.15. We were asked to find the probability of H given C. So using the formula, that probability is the probability of H intersect C divided by the probability of C, which once again is 0.15 over 0.20, which comes out to, again, either 3/4 or 0.75. All right, now in the case of equally likely outcomes, it's maybe just a tiny bit simpler. In the case of equally likely outcomes, what you can do is just count the number of outcomes instead of the actual probabilities. So the probability of E given F would be the number of outcomes in E intersect F divided by the number of outcomes in F, provided that the number of outcomes in F does not equal 0. All right, as an example of that, suppose a sample of 2 balls was selected from an urn containing 8 white balls and 2 green balls. What is the probability that the second ball selected is white, given that the first ball selected was white? The number of outcomes in the first ball is white is 8 times 9, which is 72. That is, the first ball must be among the 8 white balls, and then the second ball can be any of the 9 balls that are left. The number of outcomes in the first ball is white and the second ball is white is 8 times 7, which is 56, because there are 8 ways that the first ball can be white and then only 7 ways that the second ball can be white because one of the white balls is gone. Therefore, the probability that the second ball is white, given that the first ball is white, is 56 over 72, which simplifies to 7/9. All right, that brings us to the product rule. If the probability of F does not equal 0, then the probability of E intersect F is equal to the probability of F times the probability of E given F. Notice that this is the same formula as the formula for conditional probability. It's just written in a different form. If you were to divide both sides of this equation by probability of F, you get your conditional probability formula. And this rule can be extended to 3 events like this. At some point, maybe in the next section, I will show you how to use a tree diagram. Tree diagrams often make this type of problem easier than using especially this version of the formula. All right, so for example, a sequence of 2 playing cards is drawn at random without replacement. which remember means after the first card is selected, it is not put back, from a standard deck of 52 cards, what is the probability that the first card is red and the second card is black? So let F be the event that the first card is red, and let E be the event that the second card is black. The probability of F is 1/2, since half of the deck consists of red cards. And if we know the first card is red, then that means that what remains in the deck after a red card is taken out is 26 black cards and 25 red cards. In other words, 51 cards left, 26 of them are black. So that means the probability of E given F would be 26 over 51. Therefore, the probability of E intersect F is equal to the probability of F times the probability of E given F, which is 1/2 times 26 over 51, which simplifies to 13 over 51. So just a little bit more than 1/4 chance of that happening. That brings us to independence. Now, it's very easy to misunderstand what independence means, and I think a lot of that is because of the way we use the word independent in everyday English. Let E and F be events. We say that E and F are independent, provided that the probability of E intersect F is equal to the probability of E times the probability of F. Now, that is a good formula to use when you're doing problems, but it doesn't really give you a sense of what independent means. You get that better from this version. Equivalently, two events are independent provided that the probability of E given F is equal to the probability of E, and the probability of F given E is equal to the probability of F. So what it really means for two events to be independent is that knowing that one event has occurred does not give you any information about how likely it is for the other event to occur. In other words, it doesn't make it any more or less likely. So for this, I like to use examples like, let's say that I have a group of 1,000 students, and event E is the probability that a randomly selected student is a psychology major. F is the event randomly chosen student has brown eyes. Okay, those two events have absolutely nothing to do with each other. There are lots of brown-eyed psychology majors out there, but if I say close your eyes and I'm thinking of a student, and I want you to guess whether the student has brown eyes. Oh, I'll give you a hint. The student is a psychology major. That's not a very good hint, right? Because it doesn't make it any more or less likely that the person has brown eyes. So that's really what independent means. Sometimes people think that it means separate. It does not mean separate. Separate in probability really means mutually exclusive or disjoint, and that is a completely different thing. In fact, independent events are never disjoint. All right, so you don't want to get those two things mixed up. All right, so let an experiment consist of observing the results of drawing two consecutive cards from a 52-card deck. Let E be the event the second card is black, and F be the event the first card is red. Are these two events independent? From the previous example, the probability of E given F is 26 over 51. However, the probability of E is 1/2, because half of the cards in the deck are black. Since those two numbers are not equal, that means that the events E and F are not independent. And intuitively, you can kind of see why they're not independent. If I pick a card and I look at it and I say, okay, I want you to guess whether this card is black. Oh, I'll give you a hint. The first card I picked was red. That makes it more likely that the second card was black. All right. And that's why they're not independent, because that first card being red made it more likely that the second card was black. A set of events is said to be independent if, for each collection of events chosen from them, say E1, E2, all the way up to E sub n, we have the probability of the intersection of E1, E2, all the way up to E sub n is equal to the product of the probabilities of E1 times the probability of E2, all the way up to the probability of E sub n. All right, so for our last example, all right, had to quiet the bird down. In this example, suppose a company manufactures stereo components. Experience shows that defects in manufacture are independent of one another. Quality control studies reveal that 2% of CD players are defective, 3% of amplifiers are defective, and 7% of speakers are defective. A system consists of a CD player, an amplifier, and 2 speakers. What is the probability that the system is not defective? So let C, A, S1, and S2 be events corresponding to defective CD player, amplifier, speaker 1, and speaker 2, respectively. Then the probability of C, in other words, the probability that the CD player is defective, is 0.02. The probability of A is 0.03. And the probability of S1 and S2 are both 0.07. So we want to know what is the probability that the CD player and the amplifier and both speakers are not defective. So the probability that the CD player is not defective is 0.98. The probability the amplifier is not defective is 0.97. And the probability that each speaker is not defective is 0.93. So since these events are all independent, the probability of all of those events, all of those complementary events occurring is 0.98 times 0.97 times 0.93 to the second, which is 0.822. So the probability that the stereo system is not defective is about 82%, which I have to say is not very good, right? That means that about 18% of the stereo systems coming out of there do have something wrong with them. So they're going to have to work on that. All right, so that's going to do it for section 6.4. The probability of E given F is computed as the probability of E intersect F divided by the probability of F for a sample space with a finite number of equally likely outcomes. It can be computed as the number of outcomes in E intersect F divided by the number of outcomes in F. The product rule states that if the probability of F does not equal 0, then the probability of E intersect F is equal to the probability of F times the probability of E given F. E and F are independent events if the probability of E intersect F is equal to the probability of E times the probability of F. Equivalently, E and F are independent events if the probability of E given F is equal to the probability of E. And then a collection of events is said to be independent if, for each collection of events chosen from them, the probability that all the events occur equals the product of the probabilities that each occurs. And that's going to do it for section 6.4. We'll see you next time.